Okay, let's talk about carbon NMR. This will be a complement to proton NMR, which has been, by and large, the main topic of discussion in this entire lecture. All right, but carbon NMR now completely pays attention to carbon. All right, so hydrogen is not an afterthought at this point, but the spectrometer is set up at this instance to only look at carbon. And what you may recall from the first video is that carbon 12, the most abundant isotope of carbon, actually doesn't have a spin, doesn't have a nuclear spin. Therefore, it doesn't give you a signal, an NMR signal. And to make matters worse, it is the most stable isotope of carbon. Now, carbon 13, on the other hand, that one does have a half spin, right? So you could have a plus half spin, negative half spin, depending on whether you have the up spin or down spin associated with carbon 13, same as the proton. But the problem with carbon 13 is that it's only 1% abundant. So that means that if you do have 100 molecules, only one of them will actually have carbon 13. And not only that, but the chances that you're going to have within the same molecule two carbons that happen to be carbon 13 is a lot lower, because if you consider a 1% abundance of carbon 13, divide that by 100, you get 0.01. Multiply that by 0.01 again to account for the idea that you're going to have two carbon 13s present in the same molecule, and now the value goes down to 0.0001, or in other words 0.01%. And this value is so low that statistically speaking it is pretty much guaranteed that you will not have two carbon 13s in the same molecule. All right, so what this ultimately means is that there will be no chance that you will have in the same molecule a carbon 13 next to another one, and therefore there will be no splitting. So all the carbon 13 peaks you're going to see are going to be singlets, because there is no carbon 13 next door. All right, and the other interesting thing is that the carbon 13s for the most part follow the same pattern as the proton NMR shifts that we talked about in the previous videos. So if you now look at the blue ranges right here, which are the carbon 13 NMR ranges, you see that the window is actually 10 times bigger than that of the proton NMR spectra, but the trend follows the same way. So you have your alkanes, which go from 10 to 40 ppm, followed by your alkynes, which go from 67 to 85. Now the amines and the alcohols, the carbons is what you're looking at, right? So here you have to be careful. You're not looking at the OH bond, you're not looking at the NH bond, but rather at the carbon. So they fall somewhere in a similar vicinity as what you're seeing here, right? So 30 to 65 for the amines, 50 to 90 for the carbon alcohols. And then your alkenes and aromatics fall higher in the ppm scale, or downfield in the spectrum. 115 to 140 ppm for the alkenes, 125 to 150 for the aromatics, and this tends to be pretty indicative, of your aromatic peaks. But once more, looking at the place where the peaks fall can give you an idea of what functional group you have, and the aromatics are pretty indicative. Same thing with the carbonyls. Carbonyl compounds like carboxylic acids and aldehydes show up somewhere between 160 and 200. Now, if we want to be specific, the aldehydes show up higher than the carboxylic acids in the carbon NMR spectrum. And this ultimately has to do with the lone pairs on oxygen. But um, the thing that I would want you to be aware of is just the position. So having a peak, a carbon 13 NMR peak between 190 and 200 is indicative of an aldehyde. And if you look at the proton NMR spectrum, you'll see that there ought to be a peak between 9 and 10, or excuse me, 10 and 11 for confirmation that you have an aldehyde, whereas the carbonyl peak of your carboxylic acid is going to be a little bit lower. Okay, so but in general, the trend is the same in carbon 13 as proton NMR. All right, but just watch out for that little switcheroo between aldehydes and carboxylic acids, and keep it straight. 10 to 11 for aldehydes, 12 to 14 for carboxylic acids, 190 to 200 for aldehydes, 160 to 185 for carboxylic acids. All right, now the other thing that I want to mention before we start looking at the spectra is the difference in the size of the spectrum. Like, how come proton NMR, generally speaking, goes from 0 to 10 ppm, whereas carbon-13, goes by 10 times more the value, so the hundreds instead of the tens. All right, so in order to make sense of this, you have to think about what a ppm represents. And assuming that you're using a 100 megahertz instrument, 1 ppm stands for 100 hertz worth of frequency. So if you think about the range that you have in a proton NMR, which is roughly 10 ppm, well, that will be 1,000 hertz, right? So 10 more than 100, or 100 times 10 gives you 1,000 hertz. And that's the range that you are basically dealing with for one proton. Now, when you start thinking about carbon, well, you don't have just one proton in the nucleus, you have 6 protons. So it's not that unreasonable to think that for carbon-13, the frequency will have to be 6 times as large, just because you have 6 times more protons per element, right? So this will be about 6,000 hertz based on the idea here with the protons. But then there is something known as the Lamar frequency, which is kind of like the reference frequency associated with each isotope. And for hydrogen, that's actually 100, and carbon-13 happens to be 25. These are constants associated with each one of the isotopes that we're dealing with. But all you do basically is look at the overall range in hertz, and if you divide that by the Lamar frequency, that gives you the window in ppms that you're going to have. So if you divide 6,000 by 25, you find out that this equals about 240, and then that's the window that you see for carbon NMR, just because you have more protons available in the carbon NMR nucleus compared to that of the proton. Now for the proton, I told you that the Lamar frequency is 100. So if you divide 1,000 by 100, you end up with 10, which is your 10 ppm window, right? So that's how you end up with these values. All right, now with all that being said, let's actually look at molecules and the spectrum and see how we can determine what corresponds to what. And we go back to this molecule that we talked about before, except that now we're going to be paying attention to carbon exclusively. And just to remind you, we have a mirror plane in the molecule itself, which means that what's to the left of the mirror is identical to what's to the right of the mirror plane. So we're going to have 4 carbons, the ones in red, which are identical to each other. They are equivalent, in other words. Then we have the carbons in blue right here, which correspond to those methine carbons. And then over here we have a CH2 or methylene carbon that is unique. So you only have 3 different kinds of carbons. And much like your protons, if you have 3 different kinds of protons, you expect to see 3 proton NMR signals in your spectrum. Same thing with carbon. If you have 3 inequivalent carbons, you expect to see only 3 peaks in your carbon NMR. And so this is kind of the beauty of carbon NMR. You don't have the splitting going on, so it makes it a little bit less complicated than proton NMR, but at the same time a little less informative. But the one thing that you do get from the carbon NMR spectrum is the fact that all the peaks that show up on your carbon NMR is exactly how many inequivalent carbons you're going to have in your molecule. Not the total number of carbons, mind you, but the total number of inequivalent carbons, right? So we have 3 inequivalent carbons, we got 3 peaks right here. And based on the oxidation state, we know that the carbon over here has 3 H's because it's a methyl group. So we know the oxidation state is 3 minus. The carbon over here has 1 H to complete its octet, so we have a 1 minus oxidation state. And the carbon down here has 2 H's with a 2 minus charge. So the one that is most oxidized is the blue carbon, or carbon B. So we expect that one to show up farther downfield. Carbon A has an oxidation state of 3 minus, so that's going to show up the most upfield, because it has the most electron density. And then the carbon with the 2 minus charge is going to be right in the middle. So that's one way in which you can identify which one of the carbons corresponds to the ones in your molecule. Okay, so we'll do another example. We're bringing back this molecule that has the aldehyde and carboxylic acid associated with it. And here the aldehyde is not the same as a carboxylic acid, so this creates no symmetry plane whatsoever in this molecule. So that means that all the carbons are inequivalent, every single one of them. There is no symmetry plane whatsoever, or any symmetry elements that could decrease the value of inequivalencies. So we have 8 inequivalent carbons, so we expect to see 8 separate signals in the NMR, the carbon NMR spectrum of this molecule. So let's take a look at it. All right, so here we have one signal, and this is above 190. All right, so that peak at 190 has to be the aldehyde peak, right? So the aldehydes fall between 190 and 200. The carboxylic acid peaks fall between 160 and 180, right? And then so we have this peak here above 160, a little below 170, but that's your carboxylic acid peak. So we got those two accounted for, right? So we got the peak over here and the peak right there accounted for, aldehyde and carboxylic acid. And we know that just by looking at the functional group. Now the other peaks are a little bit more difficult to assess, at least just with a carbon NMR spectrum on its own. There's other ways of identifying each one individually, but we're going to try to make it simple for now. So we could say that, all right, D and E, those carbons are, not interacting with the carbonyls all that well. If you draw resonance structures, you'll find out why that may happen. But the electron density is kind of getting withdrawn from those positions, positions D and E, also known as the meta positions in your aromatic groups. Now B and C, which are close by to the carbonyls, are kind of intermediate, and then F is the one that's farthest upfield, possibly. Now, this assignment, I should tell you right now, is not the most thorough assignment. Like, for sure, that's the aldehyde and this is the carboxylic acid peak. But normally what you want to do is perform a 2D NMR experiment to figure out what each one of these peaks will correspond to. And with that 2D NMR data, you can actually figure out which one of the peaks is what. But the thing to pay attention to is that if you count the number of peaks, you have 1, 2, 3, 4, 5, 6, 7, 8. 8 inequivalent peaks for 8 inequivalent carbons present in the molecule. All right, so let's do another example. Okay, so now we have 2 pentanol, and because of the presence of the hydroxyl group, we don't have any symmetry elements present in this molecule. There's no mirror plane, nothing that we can do to arise at equivalency. So all 5 of the carbons happen to be inequivalent. So we expect to see 5 peaks on the carbon NMR spectrum. And because none of them are alkenes, aromatics, there's no carbonyls, all the peaks fall between 0 and 80, right? Which is the range where you typically will see these peaks. All right, so 5 peaks, 5 carbons, right? All right, so the peak that is farthest downfield is the one that has to encounter the most electronegativity, electron withdrawal. And that happens if you have a highly electronegative element bound to you, like oxygen. So this will tell you that carbon B right here ought to be the one that's farthest downfield because it's directly bound to a really high electronegative element. And then that means that A and C, which are next door to that carbon that bears the hydroxyl, ought to be the next set of carbons that appear in the spectrum, so the in between. So this peak and that peak are probably A and C. We're going to figure out which one is which. So one way to tell, and now I'm kind of highlighting right here, so the peak right here, I'm saying that's the blue peak, so that's carbon A. Now one way to tell that that's going to be the case is because, first of all, A and C are closer to the oxygen than D or E. But the way in which you tell them apart is by looking at the oxidation state. The oxidation of this carbon is going to be 3- because that's a methyl group. This one is a methylene group. It only contains 2 hydrogens, so it will be 2-. So the 2- is more oxidized. You expect that one to appear farther downfield than the more reduced carbon, which will be the blue assigned peak right here. And then similarly for the peaks over there, this carbon is 2 minus in oxidation state, that one's 3 minus, so you will expect that E will appear the farthest upfield in the spectrum because of the charge and the fact that it's the farthest away from the electronegative element. So these are the ways in which you can determine which one of your peaks are what. Okay, and with all that information said, we've basically covered all of the aspects of NMR that you need to know to be able to successfully determine the structure of your molecules. Now, what I would recommend that you do in the future is practice problems, look at spectra, and use the spectra to determine the molecular structure of your organic molecule. That's basically the core of this chapter. So practice, practice, practice makes expert. And hopefully with the information here, you have enough info to tackle these problems. Okay, so that being said, thank you for watching and see you in the next series.